All right, chapter 4. This is 4.1. All about functions. Where's my pen? All about functions. And we're going to do some operations. Add, subtract. We're going to do some compositions, division, multiplication as well. Reflecting, symmetry, inverse, and then we're going to form some functions with verbal descriptions. Fun. All right, a function is a correspondence or a rule that assigns every element in the domain to exactly one element in the range. So you have domain numbers, which are inputs, and range numbers, which are outputs. And you have some rule, and it shows the correspondence. You got x coordinates and y coordinates. Okay, so this one here is not a function because each element of the domain is not paired with exactly one element in the range. 5 ruins it. 5 has 3 different ranges that it corresponds to, so it is not a function. Okay, so it would have to look something like this. I don't know, maybe we have some stuff missing, it corresponds here. This one goes over to there. Maybe we have a dot here that goes over to there. That would be a one-to-one correspondence. Every element in the domain is paired with exactly one element in the range. Give the domain of each function. A lot of times, most of the times, when we're trying to find the domain, what we're actually benefited by is finding what cannot be in the domain and then say the domain is everything else. Okay? For instance, this first one, this denominator can never be 0. So we know that if x minus 7 equals 0, we got a problem. So it can't equal 0. So we would add 7 to the other side, so x cannot equal 7. So the domain, you know how to do the interval notation. This would be a set builder notation, just to give you just different options. Set of all x such that x cannot equal 7. Okay, it's read set of all x such that x cannot equal 7. That carries it. Letter B, square root 1 minus r squared. Well, we know that the square root cannot be negative, so it has to be greater than or equal to 0. So we're going to solve, well, actually inside has to be greater than or equal to 0. Let's see, greater than or equal to 0 it has to be, right, in order for it to work. So square both sides. 1 minus r squared greater than or equal to 0. Take r squared to the other side. R squared. And then this is an inequality. It's squared. So we're going to solve this one, which gives us r equals plus minus 1. So we have a negative 1, sure. 0, a positive 1. Equal 2, and let's see, can 0 work? If I plug 0, then we need to go back into here, the original. So is 0 squared smaller than 1? I think it is. That's true. And you can do another test if you want. Out here at 2, well, 2 squared is 4. 4 is not less than 1, so this is false, this is false. So we have to be in between here. Set of all r's such that negative 1 less than or equal to r less than or equal to 1. So that says the set of all r's such that r is between negative 1 and 1. That is the domain. Okay, analyzing a graph of the function, and this is exactly what I try to do. If I have a graph especially, is I look to see what I call where does the graph cover the x-axis. So you can see it kind of starts there to there, and we have all this in here. So that would be where the domain lies, and then a bluish greenish color here, in between here and here is where the graph covers the y-axis. So this would be the range, all of this stuff in between there and there. So I look to see where the graph covers the x-axis, where it covers the y-axis. And of course, zeros are x-intercepts. Use the graph to find the domain, range, and zeros of the function. Domain. All right, so there are not any arrows on the end of this. graph. But if I were doing this graph, I would assume that this graph is going forever that way and forever this way. So I would say all real numbers. Real numbers. If you're into the notation, reals and integers and wholes and naturals, that'd be the capital bold R. At least the best that we can do it. Not having bolding or any types of italicizing. Range. Range is, well, the range bottoms out here at -1 and it tops out there at 2. So you do set of all y's such that -1 never gets to -1. So I'm going to let less than, what's our letter? Y. And then I'd say it gets all the way up to 2. Okay, zeros. 1. 1. It's a 1. Okay, x equals 1 if you wish. Next problem. Domain. Okay, so we're starting here, not included. And again, we would assume that this continues in this downward trajectory in some sort of smooth curve. It's not showing that it comes up, so we can't assume that it comes up, but we can assume that it continues downward. So the domain is going to be set of all x such that x is greater than 1. Range. Well, the range, again, this goes down on the right end forever and ever, so -infinity, and up to 3. So a way of writing that was set of all y's such that y is less than or equal to 3. Zeros. Zeros. 2, 4, 6. You can go x equals if you wish. Vertical line test you should be familiar with. I say it a little bit differently than this one is. I do a vertical line test is if a vertical line can be drawn through the graph and it touches that graph in more than one place, then it is not a function. Okay, so here is everywhere we go, only once. Yes, function. Here, one time, probably about right there, hits twice. Not a function. Okay, vertical line test. Gotta love it. Okay, vertical line test. Is it or ain't it? This is no. Touches twice. This one, be careful. The open circles are open. So anywhere over here, I'm sure you can tell pretty easily that those are all places where, and you may get tripped up here. But if I draw a vertical line through here, I only touch the graph in one place because down here, I'm going through an open space. So the line is not touching there. So this is, yes, it is a function. Function. Okay, they wish us to give the domain. Let me clear out some of this stuff so I can see what my numbers are. All right, domain starts here. That's a solid dot on the end. It does not go any further. Ends here. That's a solid dot, does not go any further. So the domain would be set of all x such that, all right, so this is a -1, that's -2, 1, 2, 3, 4, 5, 6. X is between -2 and 6, so -2 less than or equal to x, less than or equal to 6. Range. Looking at the y's now. So the y's, might probably change colors. Y's go this way, there to there. It does come down to here, doesn't it? It comes down to here. Okay, it stops there, doesn't go on further and further. Set of all y's such that. Okay, the smallest number is -1. It appears as though it's equal to, so I'll go less than or equal to y. And it goes up to 1, 2, 3. But it's open, so it doesn't never get there. So we just do less than 3. Okay. 6 is, yes, it is a function. All right. It is continuing, domain, all reals. Range. Run out of space here. Range is, well, looks like we top out here at about 2, and we bottom out here at -2. So I would say set of all y such that -2 less than or equal to y less than or equal to 2. Okay. Give the domain. Find what is not in the domain, and then say it's everything else. Bottom equal to 0. Can't divide by 0. T equals -3. So t cannot be -3. Set of all t such that t is not equal to -3. All right, bottom equals 0 again. So we have a t plus 3 and a t plus 2. So in the original form here, we have t equals -2 and -3. In other words, can't be -2 or -3. So we'll have to go, let's see here, we have to go, let's see, set, these messages throwing me off. Set of all t such that t cannot be -2 or -3. And lastly, same thing, we're going to get 0 plus and minus 3. So set of all t such that not 0, not plus or minus 3. Give the domain range in zeros. Okay, so this one's radical. So we have square root of t. Square root of t has to be greater than or equal to 0. Square both sides. T has to be greater than or equal to 0. That's your domain. All right, now the range. This is where we get tricky here. All right, so as I'm trying to talk and write down the domain in fancy schmancy notation. All right, so as we start with 0 and start plugging in numbers for t, start 0, 1, 4, 9, 16, 25, 36. We start plugging those numbers in, you'll notice that this graph is increasing. Okay, so the numbers are increasing, the f of t is increasing. So we would say the range is y's, I guess, such that, see, we're going to get greater. The smallest we get 0, plug in 0, you get 0, square root of 0, 0, and really everything bigger than that. So how about we go y greater than or equal to 0? So this was the domain, and this is the range, and the zeros, they asking for that as well. And the zeros, Z-E-R-O-E-S, 0 is 0. All right, now 9 minus t squared. We got a little family graphs here, don't we? What's going to happen? We know that 9 minus t has to be greater than or equal to 0. Take t to the other side. 9 greater than or equal to t, or t is less than or equal to 9. Okay, t less than or equal to 9, that's the domain. So set of all t such that t is greater than or equal to 9, domain. Range, okay, wow. What's this graph doing? Whew. Can we plug 0 in? Can we plug 3? Can we plug, sorry, I was trying to get a perfect square here. 4, 1, 9, 16. What in the world's going on? Okay, well, obviously we cannot do that. But what's the graph doing? Because we could plug in -50, we'd still be okay, because 9 minus -50 is still radical 59. So that's still okay. So what's happening here? Do you remember the graph of the square root function? It starts at 0, 0, and 1 and 1 is on your graph, and 2, 3, 4, and 2 is on your graph, so forth and so on. This is kind of like this half parabola going sideways up this way. What's the 9 minus t do to this graph? Well, the 9 minus t does. We know that our domain has to be less than or equal to 9. 4, 5, 6, 7, 8, 9. Okay, so that 9 minus t starts us here. We can't go bigger. We got to go smaller. So it is in some way, shape, or form this graph here. Okay, you should be able to tell from there that the range is everything greater than or equal to 0. Set of all y such that y is greater than or equal to 0. And the 0 is 9, if that's possible. The 0 is 9. All right, what does 9 minus t squared do to our graph? Gosh. Okay. Well, our domain, let's look at our domain. We know that, let's see if I have space. I have space over here. I'm going to go up a little bit. 9 minus t squared has to be greater than or equal to 0. 9 greater than or equal to t squared. Okay, if we put an equal sign in there, we get these critical numbers plus and minus 3. Not t squared anymore, t. Number line, -3, 0, 3. Putting 0 into the original up here, we get 9 greater than or equal to 0. Yeah, 9 is greater than or equal to 0, so that's true. It's false out here for all the reasons that we've learned in the past. And it should be a solid dot. So our domain is only in between 3 and -3. Here and here. Interesting. Okay, what happens when we plug in numbers 3 to -3? Well, we plug in 0. 9 minus 0 squared, I'm going right into here. 9 minus 0 squared is 9. Square root of 9 is 3. 1, 2, 3. So we get that point. So we end up, really, do some more investigation, you'll end up with this semicircle as the graph of 9 minus t squared. So the domain is still, in between 3 and -3. The range is between 0 and 3. And the zeros are -3 and 3. Lots of 3s. Okay, so just interesting tidbits to maybe know about a graph. Sketch the graph, use it to find the range and the zeros. Okay, 14, vertex form, vertex. Okay, vertex is HK, 3, 4. Okay, so 1, 2, 3, 1, 2, 3, 4. This is a -a, it opens downward. Okay. And it opens downward in a special way. I don't know that we've talked about, but if I move over one space and I square 1, I get 1, so I can move down 1. Now, the fun begins here. If I move over 2 spaces, 2 squared is 4. I can go down 4. 1, 2, 3, 4, which coincidentally enough, on each side, because of symmetry, coincidentally enough, is our intercepts. Okay, and you can continue that as far as you wish, graphing a parabola. I could go over 3. I could square 3 and get 9. Go down 9, 4, 5, 6, 7, 8, 9. So I would be here. And symmetry gives me this point over here. Y-intercept is 1, 2, 3, -5 according to that. Did I miss it by 1? Must have missed it by 1. Oh, I did. Yeah, this dot goes over. Scissors. This dot goes over here. My bad. This dot goes over here. Okay. So there. Oh, I messed up. Boy, I messed up again. Oh, I did 1. No, that is 2. That is right. I was right. I could not possibly be wrong, could I? All right. There we go. All right. I think. Yep. That looked good. So the y-intercept would be -5. Did we get 1, 2, 3, -5? So if I plug in 0, I get 9 when I square it. 4 minus 9, -5. Bingo, it works. Okay, so just a fancy schmancy information about parabolas and graphing. I love to show my students. And what I say is kind of slope. kind of slope? Ask me in class. We'll go deeper into it. All right, so the range is everything less than 4. Range set of all y such that y is less than or equal to 4. That's our max point there. And not Max Clausen, but max point. And then we have 1 and 1, 2, 3, 4, 5. I hate these small graphs. 1 and 5 for zeros. All right, here you're going to factor. Okay, you're going to factor. You're going to get t squared times t plus 4. Take out a negative 1, t plus 4. And then we're going to have t plus 4 times t squared minus 1. It's going to give us negative 4. Plus and minus 1 are our zeros. All right. Question is, we really don't know what's going to happen in between. Somewhere it has to go up and down. 1 and 1, 1 and negative 1. And the other one was what? Negative 4? Negative 4. 1, 2, 3, 4. Okay, range is going both directions. See, we don't know yet how to find this maximum point or this minimum point in order to get the range very well, but we have the intercepts. Okay. All right, piecewise function. All right, all this does is it breaks this graph into pieces. Just do the first one first, second one second, third one third, and you'll be fine. So if u was less than 0, this is 0. Where's our graph? Well, what I do with these, I just graph them. Y equals, and if you want to change it to x minus 1, you can. It has a y-intercept of negative 1 and a slope of 1 up 1 over 1. And then we would draw that in like that. And our domain restricts us to less than 0. And then we get the eraser out and get rid of that part. And then keep that. So that's keeper for this part, other than we would have an open circle here. So what I do is I just make a bigger circle. So I already have a dot there. Okay, u squared minus 2u minus 3, that's a parabola. Negative b over 2a. Negative b over 2a. That's 1. Comma, plug in 1 minus 2 is negative 1. Minus 3 is negative 4. Is the 1 negative 4 is the vertex. That's handy because, well, we're going to go over to 1 negative 4. 1, 2, 3, 4. So 1 negative 4 is here. And I only draw that in between 0 and 3. So parabola opens upward. I know I'm going to go to there. And I'm going to go over 1, up 1, over 2, 1, 2, over. Oh, isn't that convenient of them? So I would stop right there. And 0 for greater than 3. So 0 greater than 3. There's the graph of 0 greater than 3. There is your piecewise defined function. Should be review. Have fun with that. It is quite interesting stuff. The parabola graphing. Ask me in class. And have a great day, and I'll see you soon.